Right, this is the setup we're going to use to verify Newton's second law of motion, and in particular the equation force equals mass times acceleration, so F equals ma. Right, the mass we are going to accelerate is this cart here, okay? It's got wheels on it and it goes on the track like that. Now, we need to accelerate it using a force. So there's a piece of string attached and we have some slotted masses, some 10-gram slotted masses over the edge of a pulley. Okay, so as we can see, the cart will accelerate. Okay, right, now the force that's doing the accelerating, we can calculate quite easily, because if we know the mass of the slotted masses and convert that mass into grams, we can calculate that as a value of weight. So the weight of this is going to be the accelerating force in the tension in the string. Okay, so that's how we're going to measure the force. Right, this is the complicated bit. How are we going to measure the acceleration? Right, well, we're going to do it electronically. Two light gates, two wireless light gates, and a laptop running the software, the data logging software. Okay? Now, on the card, you might notice there's a piece of card. Okay? Now the card, that's called the interrupt card. Okay? The way light gates work, there's a light beam going back and forth between here. Now, when the cardboard breaks the light beam and goes through and lets the light beam go back again, the light gate and the data logger, they can time the exact time for the cards to go through the light gate. Now, if we know the width of the light gate, the computer does a simple speed equals distance over time. So speed equals distance over time it breaks the light beam for. So we can have the speed here, we can have the speed here, and another thing that the data logger does on the laptop, it also measures the exact time between them. So if we've got speed here and we subtract speed here and divide it by the time to go from here to here, we've got the acceleration of the cart as it goes through. Okay, now what I'm going to do, I'm going to do the experiment with a range of slotted masses, and we're going to measure the corresponding accelerations. Right, you might want to have a look at the screen here, okay, because you're going to write down these values. Right, this is initial speed u, this is final speed v, this is the time between, okay, and this is the acceleration, the actual acceleration. Okay. But one thing before we start though, we need to compensate for friction in the track. Okay? Now, we can set up this little, we can adjust the height here, or we can adjust the height here. Because we only want the acceleration due to the tension in the string. We want there to be zero acceleration when it's moving without any force acting. So, if I just give a push and let it move through, okay, we notice that the acceleration hasn't changed because what have I done? I've not pressed start. Right, let's try again. So if I let it go, right, so we've got a negative acceleration. A negative acceleration is a deceleration. So if it's decelerating, okay, that's because of friction. Right? So we want to tilt it slightly up like this, because we want zero acceleration. We want the cart to be moving at a constant speed. Let's go again. You ready? Still the same. So let's tilt that up. Right, let's try again. Okay, so we want the cart to be moving through, we're getting there at a constant speed. Almost. So close. That'll do. Right, we now have the cart moving through constant speed. That's just to stop it accelerating. So let's get ready. Now one last thing. The independent variable here is the accelerating force F. The dependent variable is the acceleration, which we're going to measure. We need to keep everything else constant. Now there's another variable in the equation, and that is the mass. Now the mass of the trolley stays constant, but the thing that gets accelerated, okay, is the whole system, i.e. the slotted masses and the mass of the trolley. Okay? So what I'm going to do, whenever we take a mass off here, okay, I'm actually going to work backwards. We're going to start with maximum weight here. So every time I take one off here, I'm going to stick it on the cart. So if I reduce these masses, I'm going to make sure they go into here. That keeps the mass of the system constant. Right, first one for you to write down. So our first, like I said, we're going to work backwards here. Right, we're going to start. We're going to start with the maximum weight. Now the weight on here, we've got eight of these 10 gram masses. So we've got 8 lots of 10, we've got 80 grams. So our accelerating mass is 80 grams. You need to convert that into a force in newtons. Okay, so we're going to start with 8 here. Like I said, every time I take one off here, I'm going to put it onto there. Right, are we ready? Ignore the... Let's go. Right, so this is the first data point. Right, 1.21 meters per second squared. 1.21. Right, I'm going to take one off and put it there. So I've now got 2, 4, 6, 7. Okay. So this goes onto there like that. Stick that down. Back to the start. We're now going to go with 70 grams. 70 grams is the accelerating mass. New acceleration. 1.06 meters per second squared. Going to take one off, put it down there. We've now got 6. 1, 2, 3, 4, 5, 6. Okay. Right, 60 grams as the solid masses. New acceleration is 0.91. Now I'm going to leave it with 5. Take one off. Stick it on there. New acceleration, 0.76. Take one off. Now 4 slotted masses left. Don't forget to place that one there. So for 40 grams is the accelerating mass. New acceleration 0.61. Right, what have we got? 30 grams left there. 50 extra grams I put here, if you remember. Right, new acceleration. 0.46. $20 grams left. 20 grams. Okay, I'll make this the last one. Make this the last one. Because obviously if we go down to 0, we're going to have no accelerating force over it. I'll make this as the last one. So 20 grams is what we have. And our final value of acceleration is 0.30 meters per second squared. Right, so that was varying, making the accelerating force as our independent variable, and the acceleration was our dependent variable. We could have done this a slightly different way. We could have kept the accelerating force constant, i.e. we could have kept the slot of masses constant and varied the mass of the collision cart and the trolley. But one last thing is, what about the mass of the collision cart? Okay. Right, I'm going to show you in the lesson how to find the mass of this guy. Okay? Thank you.